We're going back to look at fluid pressure now. We skipped this earlier because there's no new math in it. It's just an application to fluid mechanics. It's a very simple one. This is a very easy section. There's one formula. There's no new math in it. Pretty good, huh? What is a fluid? A fluid is a substance that flows to conform to the boundaries of any container that includes liquids, and it also includes gases. In this section, we're going to confine ourselves to incompressible fluids, such as water. If you fill a bag full of water and it takes up 1 cubic foot of volume, and then you take it underwater, because water is incompressible, it will still take up a cubic foot volume when it's submerged, because what happens is the force of water just gets bigger and bigger and bigger, but the atoms stay the same distance apart. They just push harder back to keep from going in. And so that's what we're talking about here, is incompressible fluids. And the concept of pressure works like this. It's a force per unit area. If you take the force, if you have a total force on say a plate that's submerged in water, and it's the same force at every point, then you just take force divided by area as the pressure. And so it has units of like pounds per square foot or newtons per square meter, depending on the units that you're using. All right, I'm going to cut through a bunch of this stuff. I dislike this particular section. This is a great book in general, but this section is not, in my mind, the best. I'm going to cut to the quick. When you submerge a plate horizontally in a fluid, what you find is that the force on that submerged thing is equal to the weight of the water sitting vertically above it, or whatever fluid it is. So that when you put a horizontal plate 10 feet down, and it's got 100 square feet area, then there's 1,000 square feet of water above it, and so you take that 1,000 square feet of water and multiply, cubic feet of water, I'm sorry, and the 1,000 cubic feet of water and multiply it by 62.4 pounds per cubic foot, and you get the number of pounds of water, the force of the water pushing down on the plate. Now, suppose you turn it vertically like this. Now it's a different game, because the pressure at the top is different than the pressure at the bottom, right? There's more water sitting on the water down here than there is on the water up here. That's actually the only fluid we're going to do in here, is water. It's just trying to keep it simple. What do we do? Well, so we can think of partitioning the x-axis, x0, x1, down to xn, going from A to B, and on each of these little sections we can find the force on this part, the force on this part, the force on this part, add them all together, we'll get the total force on each side of the plate. And so if at the kth interval, xk minus 1 to xk, we have a width of delta xk, I'm sorry, a length of delta xk, and a width of w of xk star at some intermediate point xk star. We'll get this approximate area here, height times width, and then if we multiply that area in whatever square feet times the pressure in pounds per square feet, we get the force of water pushing at that depth horizontally. And so we'll call the depth h of xk star, and the x-axis goes downward, positive downward, and actually, and this is one of the things I dislike about the book, if you put 0 at the surface of the water, if you put x equals 0 there, then h of xk just becomes xk. And all this just simplifies. So the force when your xk star feet down is rho xk star ak. You just replace h with x. Now, how do you find the total force of the water over the whole plate? This is the approximate force on the kth piece, is the area times the height times the density function gives you the pounds of force or newtons of force. But when you take the limit of the sum of rho h of xk star ak, you get, of course, the integral, right? That's the definition of the integral. If you take the limit of that sum. So this is the one formula for the section we've just derived, is force equals the integral from height A down to height B. Remember, x is positive downward. Rho, the constant density, times, this is just x, provided you put x equals 0 at the surface, times the width of the lamina gives you, integrated with respect to x, gives you the total force on the lamina. This is the limit of the sum of the forces on those little pieces approximated. You can make those actually exact if you pick x k star correctly. And so here's an example. Suppose you have a dam that's 100 feet height and a constant width of 200 feet. Find the total fluid force exerted on the face when the water surface is level at the top of the dam, and let's say we put it at 0. So let's put this out so you can see the picture here. Then we're going to integrate from 0 to 100. Right, we're supposed to integrate rho HW. Integrate from 0 to 100, the top down to the bottom. 62.4 is the pounds per cubic foot is the weight density of water. That's different than mass density, right? It's not like in the international system, kilograms per cubic meter would be mass density. Newtons per cubic meter would be the weight density. That's have to multiply. They differ by the factor of 9.8 meters per second squared acceleration of gravity. Here pounds is a force actually, so it's 62.4 pounds of force per cubic foot times x, the depth, times 200, the width, dx. Integrates to 12,480 integral from 0 to 100 x dx. Comes out to be 62,400,000 pounds of force. Fortunately, it's spread out over the whole dam so it doesn't burst it, right? So that's the easy problem, just to get started. And then there's a few problems in the text I just want to introduce you to. I think you'll find these straightforward. It starts off actually with a horizontal plate instead of a vertically submerged plate. Suppose it's submerged this way with water sitting on top of it. Find the force in pounds and the pressure in pounds per square foot on the top surface of a plate if its area is 100 square feet and the surface is and the plate is at a depth of 5 feet. Well, again, it's just the total weight of the water sitting on top of it. It's 100 square feet area and then 5 feet of water thick above it, so it's 100 times 5 or 500 square feet of water sitting over the plate. If you multiply that volume, 500 cubic feet, times 62.4 pounds per cubic feet, you get the pounds, 500 times 62.4, whatever that comes out to be, pounds of force pushing on that plate. Similarly, newtons and pressures in pascals. If the surface area is 25 square meters for a horizontal plate, and it's a depth of 10 meters, then there's 250 cubic meters of water, multiplied by 9,810 newtons per cubic meter. It's just 250 times 9810, whatever that comes out to be, is the force in newtons on the plate. On the top of the plate and the bottom, because the water below is pushing up and the water below is pushing down. And so it's not going to bend the plate, it's going to crush the plate, is what's going to happen if the plate is not strong enough to withstand that. And then the pressure is just that force divided by the 25 square meters. And up here, the pressure is the force divided by the 100 square feet. All right, now the interesting problem here, number 7. This is the only hard problem on your homework assignment, and it's not very hard. There's just one formula. You say, what could be the total force pushing on each side of this plate that's got a variable pressure, right? At the top, it's only 2 meters down. At the bottom, it's 10 meters down. 6 by 8 by 10, 3, 4, 5 triangle times 2. Triangle, how much force is in there in newtons? Well, here's the picture. If you put 0 at the surface level and run the x-axis down the edge of the rectangle, that's the easy way to do it. Half the problem really is just setting it up easy sometimes. Then the plate goes from 2 meters down to 10 meters down. And we just have to integrate then. A to B, rho, x, w of x. I replaced there h with x, since I put 0 at the surface level. Rho, x, w of x dx. And A is 2 and B is 10. That's where the surface begins, or the plate begins and the plate ends. Rho is constant, 62.4 pounds per cubic foot everywhere, since it's incompressible. It's got the same density in any depth. Times x, the width, the depth, times the width is, well, that's the hard part to figure out. We have to figure out the equation of this line. At a typical depth x, the width is the y-coordinate of this line. I have to think of x going this way and y going this way, right? So that's the hard part of the problem. Well, it goes through the point 10, 0, x equals 10, y equals 0, and it has slope. Well, it goes down 6 for over 10, minus for over 8, minus 6/8, so put point slope formula, y minus y0 equals m minus 6/8 times x minus x0, with the point x0, y0, 10, 0. Now that reduces to y equals minus 3/4 x plus 15 halves. So we put that in for the width at any depth, and now we just have to do this simple integral of a polynomial. We can pull the 62.4 out and integrate from 2 to 10. Minus 3/4 x squared plus 15 halves x. And if you run that in your calculator, I did that just to show you what I got here. Let's see. Turn this thing back on for a second. You get 1,098,720 pounds of force. Pounds. Newtons. Since we did metric units. Pushing against each side of the plate there. Here's what you can do in your calculator to do those simple integrals, just to remind you. I just put in this command, 9810, from the keyboard, times, to get the integral, you just push second 7. Maybe I better zoom that out just a little, huh? It has the integral sign in yellow over the top. And I'll put in the equation, minus 3 divided by 4 times x squared plus 15 halves times x. I'm going to arrow this over here a little bit, you can see the rest of it. Comma x means with respect to x, comma 2, comma 10 means from 2 to, integrating from 2 to 10, close the parenthesis. Shows up, is the way you write it by hand up here and calculates that number. So try those, I think they're real easy this time.